Peace be upon you. My name is Muhammad Laiq Seviki, the father of Holophase. Part 21 Algorithmic Information Production How Simple Seeds Write Complex Worlds. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are approaching the summit of Book 9.5, Computational Generation, in Episode 9. Our journey through this book has reframed our understanding in a profound way. We began by seeing phi as a programming language, its dynamical rules as instructions. We then explored a specific, elegant hardware architecture, the universe as a cellular automaton, a vast grid of simple cells updating in synchrony. This paints a picture of a deterministic, rule-bound cosmos. But a pressing and beautiful question now arises, one that has tantalized philosophers and scientists for centuries. If the universe is just following simple rules from a simple starting point, how do we get this? How do we get the staggering complexity of a rainforest, the intricate structure of a galaxy, the profound novelty of a thought, the breathtaking beauty of a snowflake? Does such richness demand an equally rich, complex starting condition, a script as long and detailed as the universe itself? Or can genuine, endless complexity arise from a simple seed? Today, in Part 21, Algorithmic Information Production, we discovered that the Holophase grammar not only allows for this, but is exquisitely designed for it. We will learn the concept of algorithmic information and see how a very short phi program, a simple initial pattern and the compact rules of the action, can generate an output of essentially infinite descriptive complexity. Our anchor image is a single, small, nondescript seed held in the palm of your hand. This seed is dry, hard, simple. It contains no tiny tree, no branches, no leaves. Yet, when placed in soil and given the simple rules of sunlight, water, and chemistry, it unfolds into a massive, sprawling oak tree with millions of leaves, a unique branching pattern, and an ecosystem in its canopy. The seed is the short program. The growth rules are the grammar. The mature tree is the complex output. The oak's complexity is not stored in the seed. It is produced by the execution of the growth rules on the seed's compact information. Today, we learn how the universe is this seed, and the laws of physics are its growth rules. Here is the deep puzzle of this part. We look at the world and see immense complexity. A complete description of the state of even a cubic centimeter of air, the position and velocity of every molecule, would require an astronomical amount of information. Does this mean the initial condition of the universe, the so-called phi of t equals 0, must have been equally complex and information-rich? Or can a universe with simple, compact initial data and simple, compact laws generate such detailed complexity over time through its own algorithmic dynamics? The answer lies in the field of Algorithmic Information Theory, pioneered by figures like Ray Solomonoff, Andrei Kolmogorov, and Gregory Chaitin. In essence, the algorithmic information content of an object, like a specific pattern in the phi field, is the length of the shortest computer program that can generate that object as its output. Let's translate this into holophase terms. The object is a particular configuration of the phi field across space at some late time t. The shortest computer program is the combination of 1. The initial condition, phi t equals 0, and 2. The laws of physics, the actions phi and the derivation rules. In our framework, the laws are fixed and universal. They are part of the programming language itself. So the variable part is the initial condition. Therefore, the question becomes, how complex, how long, does the description of phi t equals 0 need to be to generate the complex phi t we see today? The revolutionary insight is that a very short, simple initial phi seed can, under the iterative, nonlinear application of the physical laws, produce an output whose algorithmic information, when described directly, is vastly larger. The complexity is not in the seed, it's in the execution history. The universe is a complexity amplifier. How does this work? The dynamical grammar has key features that enable this amplification. Nonlinearity. As we learned, this allows interactions where simple components create new, unexpected patterns. It's a source of combinatorial explosion. Instabilities and chaos. Tiny differences in initial conditions are exponentially magnified over time. This sensitive dependence means the system actively generates information. It turns microscopic noise into macroscopic, unpredictable variation. 3. Recursive application. The rules are applied over and over at each time step. A simple rule applied recursively can generate fractals, infinitely complex patterns from finite instructions. So, a simple, smooth initial phi field, perhaps nearly uniform with tiny random quantum fluctuations, is the short program. The laws of physics, gravity, quantum field theory, etc., are the fixed, compact grammar. Billions of years of recursive, nonlinear, chaotic application later, the output is the galaxy-clustered, life-teeming, weather-patterned universe we observe. Its apparent complexity is not a sign of a complex origin, but of a deep, productive, generative process. Let's explore the triunity of algorithmic information production, the time echo of information production, the unfolding of novelty. Time is the dimension along which algorithmic information increases. The present state is a more complex program output than the past state. The time echo is this growth of descriptive complexity. This isn't about entropy, disorder, but about the length of the shortest description of the specific pattern. A homogeneous gas has high entropy, but low algorithmic complexity. It's easy to describe, uniform. A living cell has lower entropy, but vastly higher algorithmic complexity. Its specific molecular arrangement is hard to describe, except by running the long evolutionary program that produced it. Time carries the universe from simple descriptions to complex ones. The space echo of information production, the embroidery of pattern. Across space, at any frozen moment, we see the distribution of algorithmic information. Some regions are simple, an empty vacuum region, phi is constant. Others are complex, a brain, a galaxy. Phi has this intricate, non-repeating texture. The space echo is this patchwork of complexity. It reflects where the generative process has been most active, where instabilities have played out, where nonlinearities have woven intricate tapestries from simple threads. The motion echo of information production, the flow of computation. The motion of patterns, the orbit of a planet, the evolution of a storm, is the visible computation that is generating new information. Each collision, each gravitational interaction, each chemical reaction is a logical step in the cosmic program that transforms the simple seed into a complex output. The motion echo is the processing power made visible. Now let's locate this profound concept on the master tree. We are on the Algorithmic Information branch, a high flowering limb of book 9.5, Computational Generation. This branch depends directly on the computational perspective and the cellular automaton model, as it uses the language of programs and information. It enables the next and final synthesis of this book, a unified view of how simple seeds can generate not just complex patterns, but open-ended novelty, effectively creating an infinite tapestry from finite beginnings. It also provides a rigorous way to discuss the complexity of physical states, moving beyond vague intuition. To make this abstract theory tangible, let's scatter our lanterns across domains where short programs generate long, complex outputs. A near lantern from mathematics and art, the Mandelbrot set. This is the iconic fractal shape of infinite complexity. The program to generate it is astonishingly short. In essence, it is, for each point on the complex plane, start with z equals 0. Repeatedly apply the rule, z minus z squared plus c, where c is the point's coordinate. Count how many iterations it takes for z to escape a certain radius. Color the point based on that count. This tiny algorithm, when executed, produces a boundary of infinite detail. Zooming in forever reveals ever-new, intricate structures that were not explicitly stored anywhere. The colossal algorithmic information of the Mandelbrot image is contained not in the image data, but in the execution of the simple rule. This is a perfect mathematical analogy for the universe, a middle lantern, from computer graphics and biology. L systems, Lindenmayer systems. These are used to generate realistic plants and trees. The seed is an axiom, a short string like F, meaning draw a branch segment. The rules are substitutions. F becomes F plus FF minus minus FF, meaning replace each segment with a forking structure. Apply this substitution rule recursively 4 or 5 times, and you transform the short string F into an immensely long, detailed string of instructions that, when interpreted, draws a complex, fern-like plant. The genome of a tree is like the axiom and a few substitution rules. The mature tree is the output after many iterations of growth, execution. The complexity is produced, not pre-stored. A far lantern from cosmology. The primordial power spectrum. Observations of the cosmic microwave background, CMB, show a pattern of hot and cold spots that is almost, but not perfectly, scale invariant and Gaussian. This pattern is the initial condition for all structure in the universe. Remarkably, the simplest models of cosmic inflation, a phase of exponential expansion in the early universe, predict exactly this kind of pattern from an incredibly simple starting point. A single quantum field, the inflaton, a cousin of our phi, in a simple potential, starting in a nearly uniform state. The quantum fluctuations in this simple field get stretched to cosmic size and become the seeds for galaxies. The entire complex, large-scale structure of the universe, clusters, filaments, voids, can be seen as the output of gravitational evolution acting on this simple, low algorithmic information initial pattern. The complexity of the cosmic web is generated, not primordial. From the infinite Mandelbrot frontier to the branching of a fractal fern to the birth of galaxies, a unifying truth emerges. A simple rule, iteratively applied to a simple seed, can generate output of effectively unlimited richness and complexity. The information is in the process, not the starting point. What then is the specific language role of algorithmic information production within Holophase? It is the grammatical theory of complexity and novelty. It provides the metrics and the proofs that the generative grammar we've built is not just descriptive, but generatively powerful, capable of producing outputs far more complex than its inputs. It answers the question, how can the universe's story be both deterministic, from fixed rules, and genuinely creative, producing endless novelty? The core question this part asks about phi is, what is the algorithmic information content, the length of the shortest phi-based description of a given physical state? And how does that content evolve over time under the action of the dynamical grammar? We are moving from asking what happens to asking how complex is the outcome and where did that complexity come from? What does this perspective do for our understanding? It provides a rigorous definition of complexity for physical states, rooted in the underlying phi description. It explains how a universe with simple initial conditions can appear irreducibly complex. It demystifies emergence. High-level complexity emerges from the lengthy execution of low-level simple rules. It connects physics to computation and information theory at the deepest level, suggesting that information is not just a property of the world, but its very substance being processed. Now, stability and breakdown. The concept of algorithmic information is mathematically robust. However, a key theorem shows that the algorithmic information of a string is itself uncomputable in general. You cannot write a program that always finds the shortest description. This is a fundamental limit, not a flaw. In physics, this translates to the idea that we may never be able to prove that the current universe is the minimal output of some simple phi seed. There might always be a shorter, unknown program. The framework breaks down in its pure form if the laws of physics themselves are not simple or fixed, or if there is a fundamental source of randomness that is not algorithmically compressible. Yet, the success of simple laws in explaining so much suggests this perspective is powerfully valid. This brings us to our empirical mooring, falsifiability. The claim that observed complexity arises from low algorithmic information phi seeds is a bold hypothesis about the structure of physical law and initial conditions. The central claim. For any observed, statistically regular complex phenomenon, for example, the distribution of galaxy clusters, the turbulent spectrum in a pipe, the pattern of a chemical reaction diffusion system, there should exist a phi-based model with an initial condition and parameters whose total descriptive length, seed plus laws, is much shorter than a literal description of the final data. Furthermore, as we observe the phenomenon at higher resolution, the required length of the generative description, the seed plus program, should grow slowly, while the length of the direct description, the data itself, grows explosively. A concrete measurement scene, Rayleigh-Benard convection pattern formation. Consider a shallow layer of fluid heated from below. At a critical temperature gradient, the featureless conductive state becomes unstable, and a regular pattern of convection rolls or hexagons forms. This is a classic complex pattern emerging from simple physics. We conduct an experiment with a precisely controlled cell. We measure the detailed velocity and temperature fields of the fully developed pattern using particle image velocimetry and thermography. This gives us a huge dataset, the output. We also have the exact parameters of the experiment: fluid properties, cell dimensions, temperature difference. The pass condition, validation. We write down the phi-based model for fluid dynamics, the Navier-Stokes and heat equations, which can be derived from an appropriate action for a vector field and temperature field. The seed is the initial condition, a state of rest with tiny random thermal fluctuations. The program is the equations with our experimental parameters. We run a numerical simulation from this simple seed. The simulation successfully reproduces the statistical and geometric features of the observed pattern: the typical roll wavelength, the correlation length of the pattern, the transition threshold. Crucially, the description length of our model, equations plus parameters plus simple initial noise, is thousands of times shorter than the raw data file of the measured pattern, yet it generates that pattern. This demonstrates that the pattern's complexity is algorithmically compressible using the phi grammar of fluid dynamics. The fail condition, falsification. The simulation from simple random initial conditions fails to produce a pattern resembling the experiment. It might remain disordered or form a pattern with the wrong wavelength or symmetry. To match the data, we find we must input an initial condition that is itself as detailed and complex as the final pattern. For example, we have to manually imprint the exact roll positions and phases. This would mean the pattern's complexity was already present in the initial condition. It was not generated by the dynamics. If this were true for many such pattern-forming systems, it would weaken the claim that physics is a powerful complexity amplifier. It would suggest the universe's complexity is largely baked in from the start, not grown. This falsifiability ensures that the beautiful idea of simplicity begetting complexity is testable in the laboratory. Let's cultivate a practical recognition skill. You can train your intuition to recognize algorithmic information production in any process where a simple rule or seed unfolds into a rich, detailed structure that seems to contain more information than you started with. Watch a falling domino chain create a complex, swirling design. The seed is the layout of the first few dominoes. The rule is, if a domino falls, it knocks over its neighbor. The final, sprawling, intricate fallen pattern is generated by the execution of that simple rule on the seed layout. Its complexity is in the execution trajectory. Observe a snowflake forming. The seed is a microscopic dust particle. The growth rules are the laws of crystallography and diffusion in an undercooled cloud. The result is a stunning, complex, six-fold symmetric dendrite. No two are alike because microscopic variations in temperature and humidity act as tiny differences in the initial condition that are amplified by the unstable growth process into macroscopic uniqueness. Consider the evolution of a melody in jazz improvisation. The seed is a simple theme or chord progression. The rules are the musician's knowledge of scales, harmony, and stylistic conventions. Through the recursive application of these rules in real time, a long, complex, and novel solo is generated that far exceeds the information content of the initial theme. Whenever you see a process where a small cause leads to a vast, intricate, and seemingly information-rich effect through iterative transformation, you are witnessing algorithmic information production. You are seeing a short program writing a long story. We must connect this culminating insight deeply to our Holophase journey. In the previous part, we saw the universe as a grid computer. Now we understand the informational productivity of that computer. It takes a short input, the initial phi seed, and by running the immutable program of physics, produces an output of staggering complexity, the present universe. The generative grammar is not just a set of constraints, it is an engine of novelty. This resolves the ancient tension between determinism and creativity. The story is deterministic from the outside, but from within, it is perpetually and genuinely new, because the computational path from seed to now is so long and intricate that its outcomes are fundamentally unpredictable to any observer within the story. If you want to see the full mathematical derivations and exact equations behind this idea, the formal definitions of Kolmogorov complexity, the theory of logical depth, the application to dynamical systems and statistical mechanics, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and behold the completed landscape of Book 9.5. We have journeyed from computation to architecture to the very theory of information generation. We now possess a complete computational understanding of the generative grammar. It is a simple, powerful program running on a distributed cellular automaton, capable of transforming a simple seed into the endlessly complex, ever-novel tapestry of reality. In the next part, we will climb to a new height, entering hierarchical generation. We will zoom out from the fundamental computational level and ask, how does this complex output organize itself into layers? How do effective laws emerge at different scales? How can we read reality as a nested hierarchy of phi structures, from the quantum whisper to the galactic roar? This will be the bridge from the fundamental grammar to the structured, multi-scale world we actually navigate. Before we end, the mandatory zoom out to hold our scope. Algorithmic information, complexity, seeds, these concepts are still analyses of patterns in phi and its evolution. We have added no new substances. We have simply brought the tools of information theory to bear on the patterns generated by our single field. One field, phi, plus its infinite tower of derivative questions, plus the principle of stationary action, executing as a complex computation that amplifies a simple seed into a world of boundless, beautiful complexity. The simplicity of the origin is the mother of the complexity of the result. As we conclude, hold the image of the seed in your palm. It is small, hard, simple. It contains no oak, but it contains the rule for an oak, in conversation with the rules of the world. Plant it. Watch. The simple becomes complex. The short becomes long. The seed becomes a universe in miniature. The cosmos is that seed. The holophase field is the genetic code within it. The laws of physics are the soil, the rain, and the sun. And we, in this moment of awareness, are a fleeting, intricate branch, feeling the sap of that infinite growth rise within us, thinking the thoughts that the seed, at its planting, could never have contained, but was always destined to produce. Salam and peace be upon you.